Dr. Ashwath Babu is assistant professor in IIIT Harvard, Karnataka. He is a physics faculty there, and he did his PhD from IIT Kanpur, and he did a lot of work on quantum at that time. Good thing to note is from Ashwath Babu sir is from Andhra Pradesh, and he is from Hindupur, Anantapur district. So some of you who are from Rayalaseema, you'll be very happy to meet Ashwath Babu sir. So yeah, you can interact with him. And his mail ID is known anyway. It will be there on the IIT Harvard website. You can interact with him if you have any of these things. But of course, he is very punctual. He will share all the notes, and mostly what I appreciate is his line of teaching, which is mostly handwritten. So he uses one screen for writing the notes and one screen for speaking. So you will follow the lecture very this thing, and please use the chat for asking questions. He also follows the chat on another screen. So he is very interactive. So that way, and then he has taught, I would say, in all the courses, QT1 to QT7 also is going to speak. QT8 also is going to share. I think 10 also will be speaking. So most of the courses have his content with us. So you will continue to enjoy lectures by Dr. Ashwath Babu. So over to, please add. Yeah.
If you are new to this course, you will understand that sir is not only excellent in the teaching only, he is also unparalleled in the other way. That means he is also co-founder and CTO of Anutantra, which is a quantum-based company. So you understand that he has his grasp in this field, in not only in teaching, he's also in the industry. So yeah, I think the participants will enjoy a lot from this.
Yeah, one more point I wanted to add. I just remembered as Arka was mentioning, he is writing the book on quantum computation for AICT syllabus. So I think that book will also come shortly. And when he teaches QT05, he will teach from his own book. So hopefully by that time the book will come. Last time he shared a lot of material from that book. Happy learning from him. Over to you, Dr. Sumit.
Yes, Pili sir and Majumdar sir, thank you so much for the kind invitation. Sorry. And also brief introduction of me. So yes, participants, about how many are there, sir? Just to see, 430. Amazing. Right. So yeah, as you can see, the course structure, I think QT02. You might have had some introduction on quantum computing. Okay, right? So let me see what you had. Just comment. Right? So yeah. Right. So you had so far, this is 1 minute. This is the second day. Yesterday, you had introduction to superposition, entanglement, no cloning, bosons and fermions, I guess. Some kind of introduction you might have had in quantum computing. So now the question is, you can simply ask yourself or you can ask me, why the hell we have to study statistical physics for quantum computing? Right? Okay. So that's the strange. So quantum computing has to do with at the most quantum physics. Okay. And it should deal with quantum physics or some physics, linear algebra, right? But why do I study quantum statistical physics? Okay. So there is an answer here with this PPT. Okay. Right. And this PPT would answer that question. And also at the one more thing, it's very important to know statistical physics if you are going to have working in quantum computing hardware. Okay, so if you are going to work in a hardware, you need to know something more, not just programming in quantum computing. You need to know more. So what is that know more is actually described from statistical physics. Okay, right? So let me start the presentation for today. So like Felisa was mentioning, okay, like Felisa was mentioning, I would be using my presentation as well as my hand notes. Okay, so this is what my hand notes is, right? So some statistical physics we will be discussing for today. Okay, right? Wherever I would be needing my hand notes, I would use. Wherever I would be needing a presentation, I would use that presentation. Okay, right. Yeah, here if you can see the the answer is given in this slide. The statistical physics provides the fundamental mathematics or mathematical framework for understanding quantum systems at finite temperature, making it indispensable for practical quantum computing applications where thermal effects and probabilistic behavior dominate the system performance. Okay, right? So there are so many things here. Okay, let me underline them. One for sure, probabilistic behavior, which is being introduced to you. Okay, so quantum systems by me, probabilistic behavior, number one. Number two is they're so much fragile, they're so sensitive. So they're so sensitive, even the room temperature around would disturb that. So there are thermal effects which would cause them to change. Okay, right? So apart from probabilistic behavior, they are very, very fragile. Because of that, there is a thermal effects around coming from the surrounding would come into the picture. Okay, that is one. Number one. Number two. Okay, and one more thing is, okay, the one more thing is these two things would dominate the system. Okay, right? And the systems, if I'm just taking quantum systems together, just like they are fragile, they each other would affect, right? The quantum systems would affect each other even at very finite temperature. Okay, right? So somebody who just programs for them probably may not be full-fledged requirement is not there to understand what is statistical physics, but somebody who actually wanted to work on actual hardware designing when it comes to quantum computer, okay, for them it is uttermost important. Okay, so all these things, the thermal effects, the probabilistic behavior, how it would change, right, as time progresses, as it system interacts with the surrounding. So which is all actually covered in the statistical physics. It's a branch of physics which covers all these things. If you see, statistical in the sense is a probability, it's a chance, so that is there. So the moment you just say, okay, let me go shift to my, okay, the moment you say quantum qubit, okay, quantum bit, which is in short a qubit, just take, which is in fact a quantum state existing in superposition. Okay, which means at a given time when I make a measurement on the system, okay, let's say there is a measurement operator, right, which can be created out of the same basis elements. You see, there is a basis element 0 ket and 1 ket, the basis elements. For using them itself, we can construct a basis a measurement operator, which is 0 outer 0, m outer product. Okay, so this is a Dirac-Ket notation. The first one is a column, a matrix. Second one is again the matrix. Okay, how did we get? If you can see, the first one is 1 0, column, 1 0 row. Second one is 0 1 column, 0 1 row. So that is how measurement operators are constructed. Now if you just see a measurement operator acting on quantum state would give you alpha into 0. Means it puts the quantum state in the state 0 cat with a corresponding probability amplitude alpha. Okay. So where alpha is the probability number. Okay. Alpha is a probability number or a probability amplitude which is going to be dictating or telling me how many times I will get work when I make a measurement of the system several times. Several times in the sense, if I make the measurement like a system measurement like 100 times, if I make out of 100, let's say some 40 times or 40% of the time, I would get the system in 0, which means alpha square is 0.4 or point, 0.4 or 40%. Okay, right? So, right now, similarly, 60% I will get quantum state 1, so which correspond to beta absolute square. Okay, so here is the probability alpha and beta are probability amplitudes, absolute alpha square, absolute beta square are probabilities. Okay, a system is probabilistic in nature. Now the question is, if I want to process, okay, the question is, if I want to process more than 2 bits of information, okay, which means I would be needing to process, let's say, 4 bits of information. There I will take 2 qubits. As we know, 2 into 2 is equal to 4 memory locations, which would be helpful for me to process the four data points. So which would allows me to process 4 data points. Okay. Similarly, if I want to process some generic n bits of information, how many bits I would be needing? 2 to the power of small n, so that I will have which is equal to capital N. So I would be needing n qubits to process, okay, n bits of information. Okay, right? Now if you see, we are seeing here, we are seeing what we are seeing here. We are seeing here n small n number of qubits interacting. Okay, that many number of qubits are interacting means, okay, so effect of one of them affects over, okay, q1, q2, q3, q4. There are 4 qubits. They're interacting. Some of them are not interacting directly. Okay, right? So if they're interacting, okay, so if they're interacting individually with each other, fine. If the interaction of one of them is affecting the other, I should understand, okay, so there is a need for understanding, all the qubit interactions, okay, between each other. Okay, so how it is it possible? Through statistical physics. Okay, right? Through statistical physics. Okay, through statistical physics or the statistical physics one can understand interaction between the systems, between the, I'll say, quantum systems. Okay, very good. So that is what the statistical physics are saying. Not only probabilistic, they interact with each other. As we see, two qubits are interacting. Let's say example. Okay, let's say there is a quantum system A and system B. Okay, just a minute. Yeah, I'm there. I'm there. Thank you. Thank you. Okay, so the two systems, if you just see, there is a quantum system A is, let's say, alpha A 0 or beta A 1 ket. Similarly, alpha B 0 ket plus beta. Hello? Yes. Okay, okay, okay. Yeah. Okay, thank you. Okay. So beta B 1 ket. Right? So just a minute. Yeah. One minute. I'm just, that's an issue with my Bluetooth. One minute. Just give me a minute. Okay. Just a minute. One minute. I was just having some issue with my Bluetooth. Other than that, yeah. Okay. So yeah. So these two systems interacting with each other. Just a minute. One minute. Yeah. Right. So when two systems are interacting, I would be writing it as interacting like this. So tensor product. So overall tensor product between these two states is going to give me alpha A, alpha B, 0, 0. Alpha A, beta B, 0, 1. Beta A, alpha B, 1, 0. Beta A, beta B, 1, 1. This is a system I'm going to get. If you see alphas, the probability amplitudes are multiplying, going to generate new probability like alpha 0, 0, 0, 1, 1, 0, 1, 1. Okay, so the new probability is absolute alpha square, right? So these are probability amplitude, and probabilities would be absolute square of these things. Now the question is, we need to know how alpha 0, 0, alpha 0, 1, alpha 1, 0, alpha 1, 1 evolve from interaction between each of the qubits. Okay, so which is possible by studying statistical physics. That is what I meant in the first slide. Okay, right? So let's switch to the PPT. Okay, right? So the probabilistic behavior we see, the thermal effect means surrounding temperature, surrounding temperature, quantum systems interacting with each other. Okay, so that is DC. So let's go to the next part of the slide, what it says. Okay, so statistical physics is required for us. Okay, so statistical physics answer that. What is the statistical physics actually consisting of? Okay, right? If you just see, there is a many body quantum states, means we just saw there are many qubits interacting. Each qubit is treated as a particular system among the many bodies. Okay, right? So the quantum computers manipulate exponentially large Hilbert spaces requiring statistical ensemble to describe mixed quantum states and thermal equilibrium conditions. Okay, right? So large Hilbert space, what I mean is, you see, the initial Hilbert space is just a 2-qubit system. When 2 qubits interact, I have generated 4 bits or 4-dimensional Hilbert space. Okay, Hilbert space is generated. Okay, fine. Okay, okay. So let me go to the second part. Probabilistic quantum measurements. We have seen this one also. Okay. So this comes from the measurement which we discussed. So that is actually described by statistical physics, in fact. Okay. Okay. So statistical mechanics provides the Born rule of interpretation and expectation values of observables in thermodynamic environment. Okay. So let's try to understand in detail what is this. Okay. Right. So just earlier I gave you a measurement to M0 and M1, okay, and which are going to give me the measurement values. Now, what is the probability? How do I find the probability of system falling into zero? Is I just take a measurement operator on the either side, I multiply it with the quantum state. If the quantum state is made up of 2 bits, I'll get the system falling into zero state. If you can see here, okay, so if the quantum state psi is alpha 0 plus beta 1, and this will give me absolute alpha square. How? You can cross check that. Right here, the quantum state Bray representation is a alpha star beta star. Quantum state kit representation is the column alpha beta. Okay, so the P naught would be, right, P naught would be alpha star beta star 1 0 0, okay, alpha beta, right? This one gives me alpha star 0 0 alpha beta, which is absolute alpha square. Okay, so The probabilistic answer is obtained by taking some expectation value, or it is also called expectation value of m naught. Okay, expectation value, it is called expectation value. Also it is called as average value. Okay, it is just like you take the observation several times, you note down all the possible observation values and take the average of it. It will give you expectation value. This is the short notation. In fact, this is the actual expression. Okay, fine. So now if you see, the probabilistic measurements would give you expectation value. So that is actually comes from the fact of quantum statistical mechanics. Okay, and there is something called partition functions and density matrices are involved in quantum system. What is that? Let's try to understand. Okay, fine. So first of all, okay, what we want to understand, partition function, okay, and density matrix, which is actually part of statistical physics. Okay, first of all, what is a density matrix? We'll try to understand, and then we'll come to this partition function. Okay, right? So density matrix, let's say I have a collection of particles. Each particle, or quantum particle I mean, like an atoms or an electrons inside a box. Okay, collection of identical, okay, let me write down, collection of identical particles. Okay, so they are in quantum in nature, so I can represent them with a quantum state. Let's say there are two level atomic system. Okay, let's say each system is quantum state psi, two level atomic system. Now the problem is, if you, since they're so fragile, okay, so some of them are at the edges, they behave slightly deviated. Like what is the deviation? Yes, let's say there is a quantum system or a collection of quantum systems, like say in this group, okay, their probability amplitudes are in such a way 41% they exist in the ground, 59% they exist in the excited state. Okay, but what I need the all of them to behave 40%. See, ideal situation is 40% in the ground, 60% in the excited. That is what I want. But because of the interaction of the surrounding walls, there is a group which behaves slightly deviated from the actual ideal scenario. Okay, and there is one more, again it is slightly deviated, let's say 39% to 61%. Okay, so let's say they call it psi. Likewise, there is psi 3, there is another group psi 4, psi 5. Okay, and so on. I can have as many as I want depending on the slight deviation. Now you see, earlier ideal situation is all of them behave alike, means same, and represented by a quantum states. Psi is equal to alpha 0 plus beta 1, where alpha absolute square correspond to 40%, absolute beta square is correspond to 60%. That is the scenario. But because of the interaction or some other fragility of the system, there exist several groups of quantum systems, okay, several groups of quantum system, each group represented by quantum state psi1, okay, and psi2, psi2, psi3, and so on up to whatever number I have taken, let's say psi7. Okay. Now the problem is I can't represent them. Okay. I can't represent them in one equation like I was doing earlier. Earlier I was representing with one equation. Now I can't represent in one equation. For that, people what they thought, I want to represent in one equation. So let's define to have one representation, to have just have one representation. Okay, to have one representation, let's define a density matrix. What is the density matrix? We'll come to that mathematically. Let me show. So what is density matrix is, if there is a quantum state ket psi, you take outer product with itself, you would be getting a matrix. So you call it as a density matrix, letter O. So for example, here I have alpha beta, alpha star beta, which is going to give me absolute alpha square, alpha star beta, beta star alpha, beta absolute square. So this is a density matrix for you. Okay. So this density matrix, if you see it, it represents the diagonal elements of the diagonal elements, diagonal elements represent the probabilities. Okay, very good. And off diagonal elements, okay, see absolute alpha square, absolute beta square are diagonal elements. Off diagonal elements represent the polarization, or you can say existence of superposition. Okay, superposition. If off diagonal elements are 0, what you can see, system is not oscillating between 0 and 1. So this is a density matrix. So density matrix, just like a quantum state, represents about the system. Okay. Only thing, it's not a column matrix, it's a actual square matrix. Okay, right? So the density matrix captures the information of a quantum system in it. So now, can we use this density matrix representation to have representing the entire combination of this kind of a mixed system? So this is a mixed system or a mixed state. Okay, of course, yes, we can have, okay, density matrix representations, density matrix representation, okay, for each group, for each of the above group. Okay, so if I do that, what I'll have is, I'll have row 1 is psi1 outer psi1, row 2 as psi2 outer psi2, and so on. Row 7, let's say row 7, psi 7 outer psi 7. Okay, so I'll have density matrix for each group. Now I want to have representation for overall matrix, overall system represented by total density matrix rho t, which is equal to, there is a probability of any given particle existing in the system 1 group plus probability of any given particle existing in a group 2 plus so on, probability of 7, row 7. Okay, right? So this is a density matrix overall system representation. So this density matrix Fine. No. Yeah. So, right? So rho T is equal to the density matrices coming from each group were put together with the weights of probability. Means any given particle falling into particular group is associated by a particular probability P1 and P7 and Pi, something like that. So this density matrix even represents the mixed quantum system. Okay, mixed quantum system. So the mixed quantum system is handled by this density matrix. Now there is something called a partition function. Partition function is which will talk about the mixture of all these things. I would be taking a combination of all these things representing in some form of canonical ensemble, means a collection of ensemble of these systems. So that is what, okay, canonical ensemble, well, ensemble of the systems, okay, above, I would say above canonical ensemble of system is described or analyzed by partition function. Okay, partition function which is represented by Z. We'll come to that what is explicit form of partition function as we go through these slides, as we go through this few sessions on statistical physics. Okay, right? So we understood what are the three main branches of statistical physics. Okay, the foundation of statistical physics, which would allow us to understand how quantum systems interact with the corresponding mathematical principle. So here the density matrix is actually connected to partition function. How? Okay, so let me write down that expression. So the density matrix is equal to minus beta into Hamiltonian divided by partition function. Okay, so in the above I have a density matrix representation in terms of individual groups. Here I have density matrix represented in terms of the partition function, and also there is a H stands for Hamiltonian of the system, Hamiltonian of the entire system. Okay, and beta is Boltzmann constant. Okay, so this is what the last branch of quantum statistical physics would describe for us. Okay, right? So let's go further, right? So here I have the thermal fluctuations coming from surrounding temperature, which is going to give some energy exchange or going to give energy exchange between the systems. Okay, so which is explained by P of E is a distribution directly proportional to minus E by Boltzmann constant K B T. Okay, so that is what I have here in terms of the distribution. Okay, right? So what I mean by this is the existing around temperature is going to give some heat energy K beta, okay, for a quantum system. That energy is very close to the energy separation between any two atomic levels. Okay, so when I take, okay, when I just take a nucleus of an atom, the outermost orbit, okay. So then let's say I'll take a few more orbits inside so that we can take, okay. Let's say there are multiple orbits exist for a given quantum state. So let's say quantum state 0, quantum state 1, quantum state 2. As we go higher and higher, energy states are very close to each other. So the energy decreases. That is a naturally energies of atomic system would decrease as you go further away from the nucleus. What you have, the bands, the orbits are very close. They create a continuous band. Okay, sir. Okay, fine. Right now, so somebody was saying my slides are not visible. I'm sorry. I can see in my hand notes.
Sir, these are visible.
Yeah, yeah. So now if you just see, when I try to put a superposition state between, let's say, 0 and 1, okay? But because of the temperature coming from the surrounding, let's say electron goes to the above state, because of the temperature coming, the energy, sir, because of the temperature K beta, which is equivalent to H omega. So the H omega is the separation between any level 1 and 2. In that case, what happens? The electron which is at the excited state go to the another state, which I don't want that happen. And even sometime this electron would push to some other state because of the surrounding temperature. So in this way, what happens? I would lose the control over the qubit or superposition. Okay, right? Because of losing a control over superposition because of the surrounding ambient temperature. Okay, so that is what I was referring here, right? Thermal photons or thermal fluctuations would limit the coherence time and gate fidelities in the quantum processor. So, right, I was saying coherence. What I mean by coherence is when I have a quantum system or a two-level quantum system, if I excite electron from ground to excited, it stays there for 1 microsecond. So 1 microsecond is actually called a T1 time. And it stays there. After some time it comes down and it emits the whatever energy it has taken to excite and emit that same photon. Now the question is, I want to put back, I want to have a superposition. It's like fan wings are rotating. The same way, what I'll do, I'll send one more photon exactly 1 microsecond apart. So in that case, what happens? The electron which came down again goes up, right? And I will place one more photon. What is actually I'm doing? I am placing a sequence of photons in a pulse, which is area is going to have a pi by 2. So pi by 2 pulse if I send, having so many equally spaced photons, will create a superposition or put the electron in oscillation between ground and excited. This is called a Rabi oscillation. Okay, so that is what the quantum qubit state for us. Now the question is how long these oscillations would withstand. After some time the oscillations will die out, right? So if I plot time versus oscillation, the oscillations would exist for some time and then dies down. So there is a time associated how long these oscillations are existing, that is called a T2 time. Okay, so the T1 and T2 are very important for me to have a superposition. If the T1 is smaller than what is actual the pulse sequence, I would lose the ability to put them in superposition. If the type T2 is oscillation time, that is less, again I would lose the superposition time. So T1 and T2 has to be perfect or adequate for the requirement. Okay, perfection is perfect needed. Okay, so this T1 and T2 together describe the coherence. What I mean by coherence is if I just take 100 such qubits, all of them should behave in a same way, right? Let's say we took the ensemble of collection of atoms, but there is a slight deviation. Some of them vary with the probability amplitudes. Okay, so because of that, what happens? I would lose the coherence between them. It is just like we just take 10 people dancing on a stage. If few of them dance without any coordination, then it will be not appealing at all. So that is what I want to do, a quantum computation with large number of qubits. Some of them go out of the order, okay, then I would lose the ability to process the lot of information. So I have to truncate my information processing capability. Okay, right? So that is what my thermal fluctuation effect and decoherence modeling. So this is again little bit slightly advanced for you people. So how do I address the decoherence in mathematically? It is some kind of a differential equation. It is called a Lindblad master equation, which relates the rate of change of the quantum system, the density matrix variation, with respect to time to its Hamiltonian. Okay, and also there is some decay factors. So what are the decay factors? There is a decay of time t1 reducing, t2 reducing. Those things are connected by t1 is 1 over tau 1 and t2 is 1 over tau 2. These are the t1 and t2 are the decay rates. So those things are captured in this Lindblad operator calligraphy calc. Okay, so they have written like this. So overall decoherence modeling from statistical physics would allow me to encapture all the information and the dynamics of the system for the study. Okay, right. So quantum thermodynamics, what we will do, we just quickly conclude this part of the PPT and then we'll take a 5 minutes break. Okay, right? So quantum thermodynamics deals with quantum heat engines and work and entropy production, okay, and thermodynamical resource theory, okay. So if you just go through in detail, for example, quantum work fluctuation theorem relates microscopic reversibility to macroscopic irreversibility, crucial for understanding energy costs in quantum computation protocols. As you can see, quantum gates are reversible. They are microscopic, means they work on each qubit or multiple qubit. Okay, classical gates are irreversible. So they're actually acting on macroscopic system. Okay, so while working many quantum systems together may lead to a classical gate kind of operation or representation. There, how are we going to fluctuate or address these things together? Or whenever I needed, I would be needing to use quantum gate representation, and later I would be needing irreversible transformations. So there, how do we tackle these things is actually dealt with quantum thermodynamics. Okay, so that is how the statistical physics would help us to do, right? So entropy and information theory. Okay, so entropy and information theory is, again, if I just take a collection of systems, right, there is a disorderness in the system because some of them are behaving differently. So the disorderness in the system is actually connected to entropy of the system. Okay, so the entropy of the system is actually captured from the density matrix itself. So that is what the von Neumann entropy S of rho is minus of rho's trace of rho log rho. Okay, so if I represent my quantum information using quantum system, I would not have a possibility to represent them in an orderly manner. So even if I represent them in orderly manner, there is a chance I may go out of order. Disorderness will. How much disorderness is actually coming in, we need to address. That is actually possible through von Neumann entropy, is a part of statistical physics. Okay. So there are other entanglement measure just like von Neumann entropy. Okay. So other entanglement measure is like Shannon entropy. And called Shannon entropy. There is something called concurrence. So all those things are there, entanglement measures. So let me write down Shannon entropy. Okay, concurrence. All those things are the entanglement measures. In fact, they come from statistical physics. Okay, just a minute. Okay, so now we do some quantum machine learning, okay, using quantum computing. There also we would be needing the density matrix representation of all the combinations of the system, and we would be needing Boltzmann constant, will be needing partition function, all those things in a quantum machine learning. Okay, because we'll be dealing with several combinations of quantum systems. Okay, so how are we going to approximate certain approximation algorithm, use approximation algorithm? All those things are actually like possible through quantum statistical physics. Okay, right? There is a many body systems, means each system is treated as individual body. How are they interacting is also done with the statistical physics. Okay, and there is a chance that system vary between particular phases, just like a phase change. Let's say water becomes ice and then water vapor depending on the temperature. Okay, so there is a phase transition. In the case of quantum systems, there is a possibility depending on the temperature they may undergo certain phase changes. So this is very, very important in the case of, for example, these days these things are coming up. Okay, so magnetic field, magnetic property based quantum qubits being explored these days. Okay, so there the quantum phase transition addressing is going to be very, very important. Okay, right? So there is a final slide. Okay, there is a final slide before that. So there is something which is very important. The operating temperature of the quantum systems is at 50 millikelvin. Like whatever we see these days, qubits which were inside a large cryogenic temperature. Okay, so that's a millikelvin, and what we want is a fidelity very close to 100 and coherent times up to 100 microseconds. Okay, so how do you design all these things? You have to analyze and study the system using all the laws of statistical physics. Okay, so that is what the conclusion I have from these slides. So key takeaways from this PPT is, okay, the statistical physics in quantum computing is very, very useful. It will allow the mastering the thermal effects of the system. Okay, it will allow me to look for new paradigms. Okay, and it will have a guiding hardware development. Okay, new hardware I can develop with all this study. So with this, let me conclude. Why do we need to study statistical physics for quantum computing? Is we have to understand how the systems interact, how they evolve. That is possible through statistical physics. Okay, right? So having this motivation for statistical physics, in the later session we'll understand more about statistical physics from very, very simple and like crux level we'll start. Okay, right? So there is a question here by Priyaji is asking, entropy will increase in the system, then how to reduce? Okay, it's a very good question, Priyaji. So entropy means disorderness in the system, right? It is a simple, if you just take an example, let's say the students are sitting in a classroom, you lock the room, okay, and you increase the temperature of the room. So initially they sat, later on the temperature increase, they go hypothetically here and there. So increasing the temperature is creating some kind of uneasiness in the students. So they go here and there, try to figure out how to get out of that room. Okay. The same story when I take a quantum system, if we increase the temperature of the system, right? Okay. So what happens? The system will try, the particles or the systems are trying to behave hazardously. The only way to put the system in the orderly manner is cool down, okay, reduce the temperature. So that is the only way. That is why you see all the quantum computers these days, except photonic based, everything is actually needing a cooling to millikelvin. Whether you take NMR based quantum computing, whether you take a transmon or a superconducting based quantum computing, quantum hardware, all the places there is a temperature reduction. Okay, right? So I'll stop at this point. We'll take a quick break and we'll reassemble at 4:10. Okay. Yes, I think we can restart, everyone. Right. So now we have a motivation. Why do study the state of statistical physics? So what we'll now do, we'll get into the statistical physics as such. Okay. Let's get into the statistical physics. Okay. Required, remember, required for quantum computing. Okay, required. Okay, so if you just see, quantum system is a system of a superposition, a qubit. Okay, so or it can be a quantum particle, right? So not only just one particle, we'll be having several particles. So let's consider collection of several particles. I would say quantum particles. So I would not every time say quantum. So there are particles, several particles. So those particles would interact, right? Strongly they may interact. Strongly interact. Or they may interact weakly also. Means, for example, if I just take particle in air, example, particle in gaseous form, okay, in gaseous form. So where the interaction is obviously very weak. So particles in solids or in liquids. Example, particles in solid or liquid phase. Okay. So there the interaction would be definitely strong. Okay, compared to the gaseous form. So if we consider the gas particles would weakly interacting, we would say there not be much happening there. Okay, right? So for a weakly interacting case, it is sufficient to treat each particle individually, and later on we can connect them together. Okay, so in the case of weakly interacting particles, okay, what I will be doing, right? Weakly interaction, we can treat each particle individually using, okay, using a mathematical model called, or a quantum model called simple harmonic oscillator. Okay, I'll come to that. What is simple harmonic oscillator mean? Okay, so this is a thing which comes from the statistical physics. Okay, so right, so as we know, you take anything in the universe starting from example electrons or atoms, okay, or molecules, by the way, right? Okay, molecules in a composite system. Okay, anywhere if you take, the things are actually vibrating or oscillating about some equilibrium point. So that is what I would see, or anybody could see. For example, electrons, if you just see, they are revolving about the nucleus. Okay, they are revolving about the nucleus, rotating. Okay, so it is just like, let's say there is a fixed point, it is going away from the fixed point and come back to the same fixed point. Let's say stationary point. So it is just very close to having a pendulum, okay, with some mass m, oscillating about some equilibrium point. So the equilibrium point is this equilibrium point. Okay, and it is oscillating about that with some oscillation amplitude. So it is basically making a sinusoidal oscillations. Okay, sinusoidal oscillations. So just like this, electrons are oscillating. Okay, electrons are oscillating about the nucleus, so they are creating a sinusoidal oscillations. So what people thought, can we have a representation of them in the form of some kind of a pendulum, a simple pendulum? Okay, so why the simple pendulum is simple pendulum, which is in fact oscillating about the equilibrium point. So simple pendulum is going to have the total energy of the pendulum is, it will have a kinetic energy of oscillation of mv square. It will have a potential energy. Okay, so here in this case, a mass is actually pivoted from some reference point. I would say minus mg. Let's say length of the pendulum is L, so I'll have mgl is a potential energy. Okay, so the total energy is sum of these two. From there, I can assess what is this system is all about. Just like this, this is a simple pendulum. If you go to a quantum level, you will have quantum harmonic oscillator, which is just like a simple pendulum at quantum level. Okay, right? So in that way, we will treat each atom as a pendulum, and so collection of atoms together is just like a coupled pendulums. Okay, so what is a coupling? You can think of as coupling between the pendulums. You can treat it as, let's say there are so many pendulums. Okay, they are connected in between with some flexible connection. So the interaction actually comes through connector. Okay, so this is an interaction. Okay, so this is how, if the interaction is very minimal, you can almost ignore the individual pendulums. If the interaction is more, we have to treat that, bring it into the consideration. Okay, right? So very good. So this is how we are going to deal quantum mechanically. Okay, for example, let's say how a macroscopic analysis is done, right? Classical world at macroscopic level. Okay, we want to cross check quantum mechanically how we are doing, individually we are treating. Macroscopically means we put them all together and treat it as one body. So macroscopic means large bodies, collection of many individual microscopic things creating a large macroscopic body. There we will address by using what is it? We will address using position and momentum. Okay, position and momentum. Okay, so we address by position and momentum variables. Okay, so position and momentum variables, which are represented by some qi and pi's. Okay, so where pi is actually mass of the particles multiplied by its velocity, linear momentum. Okay, so linear momentum, and where vi qi is positions. Okay, so they are like xi, yi, zi, next dimension, y dimension, and z dimension. Okay, right? So now what happens if the system is having a particular description of, okay, if the system is described by pi and qi for a moment, okay, then I can always find, okay, what is the system description in slightly incremented time. What I mean is, let's say I know pi at some time t initial, qi at some t initial. If I want to find what is this pi some later time tf, qi later term tf, you can always find. So I'll take a time deviation from ti to tf, very small. Okay, so small that t final would be simply equal to small change in pi. I will add small change in qi. I would be getting that final. That much only I will change in time. Okay, so macroscopically, which is possible. Now, when it comes to quantum mechanically, is it possible? So macroscopically, it is possible, right? So if somebody is standing for some time, after some time, you may be tilted towards the right or moved a little bit towards the left, something like that, macroscopically. When it comes to microscopically, means at quantum level, is it possible to do that? Okay, right? So now quantum mechanical level. Okay, so we will be using quantum mechanical state description at that point. Now there is a one catch here. Okay, what is that catch is, okay, so when I take the quantum systems, very tiny. How tiny? They're so tiny, right? They're going to exhibit a wave nature. Remember, it is not a wave. They exhibit the wave nature. That's all. What is that wave nature? Wave nature means if you just go to a pond, let's say water body. Okay. So water body is there. If you just drop a stone at the center, what happens? It creates waves. Okay. Waves are created. Now the question is, waves are created and wave exists everywhere. Okay, wave exists everywhere. It is not fixed at one point. It is going to stay everywhere. Just like that, when I have a very tiny particle, it is going to show its presence just like wave everywhere. So quantum particle shows its existence everywhere, similar to a wave being created, right? Wave being created. So now the question is, what is the connection to the wave to that particle? Now, as we know, if the wave associated with the particle is, let's say like this, okay, so there is some wave, let's say particle is confined between unidirectional box 0 to L, Now this is a wave associated to that particular particle. Then what you do is you just take absolute square of this wave. Let's say this is a wave quantum state psi, or let's say quantum state function, mathematical function in a sinusoidal wave. You take absolute square of it. So what you're going to get is you are going to get, let me take a different color. Okay, what you are going to get is you are going to get absolute square. Okay, so this is what, okay, so this is what absolute square of a wave. Okay, so this absolute square of a wave function would give me, there is a chance that wave particle can be present at the point where there is a maximum. Okay, maximum probability. Wherever there is a wave is hitting at 0 point, the particle is never going to exist in that point. Okay, so the information of the particle and its positional information could be obtained from the absolute square of a wave function. Okay, right? Now that is one thing, and one more thing is the wavelength associated with that particle wave function is actually related to its size and its velocity. So Planck's constant divided by mass and divided by velocity. If I just take a mass of a particle just like an electron, which is about 10 to the power of minus 34 kilogram roughly, and velocity with which it can travel is 10 to the power of 8 meter per second. In that case, lambda comes out to be a few angstroms. That is 10 to the power of minus 10 meters, which is measurable wavelength. Okay, but if I go to a much larger particle, let's say a traveling bullet, so for a traveling bullet, so it's tiny anyway, it can travel with a good velocity, but the lambda d of a traveling bullet is about 10 to the power of minus 20 meters, which is not measurable. Okay, so this is the problem with the quantum systems. So quantum systems are going to have wave nature. Okay, and one more thing, so you can't exactly specify with what velocity momentum it is there, with what position it is there at a given point, because Heisenberg's uncertainty says, okay, there is always a error in the position I will be making. There is always position and momentum error I will be making when I measure, which is always greater than Planck's constant divided by 2. So this is the uncertainty principle for you. Okay, so because of this, what happens? Okay, for example, if I can divide, okay, so if I can divide, let me write a qi, that is easy instead of xi. If I want to divide the entire variable of pi, okay, so pi's are, let's say, increasing in this direction, okay, and let's say qi's are increasing from horizontal direction, okay, like that. Okay, so at any given point, let's say system is existing at some point, and later time it goes to somewhere else. Okay, so this is an initial position of a system, and this is a later time, later system state. Okay, now the system has moved from here to here. Okay, so it's moved from here to here. Now, how does it move? Probability evolve into that position slowly. Okay, but how well I divided the each unit is a question. So each unit is actually obtained by taking delta Qi into delta Pi, which is some quantity, let's say some HI unit. Okay. Remember, this unit HI cannot be smaller than Planck's constant, which means this is always larger. Okay. So there is a problem here. The problem is I cannot exactly specify the position of a particle. Okay. And I can't specify where it is located in meter times with the accuracy. So there is always some error is happening as per the statistical physics, as per the even quantum physics. Okay. So in the quantum physics, what people thought, okay, to make it more complete, so let's take a quantum system. Along with the position, you take a momentum, okay, and also represent this particles, the spin, okay, let's say spin. So there are so many particles, and there are so other degrees of freedom will be there. All those things we can take it into consideration, and will represent the quantum system using all the variables in the operator form. We will put a hat over everything, all the variables, so that becomes a quantum mechanical operators. Okay, quantum mechanical operators, position operator, momentum operator, right? This is a spin operator. Okay, so spin operators are something which tells me whether the system is having the spin degree of freedom is there. Let's say if I just take the rotational degree of freedom of the electron is revolving about the nucleus, that is the rotational spin degree of the freedom, or some degree of freedom. If the nucleus is rotating about itself, that is its own spin angular momentum. Okay, right? So that is how we are going to define the quantum systems. Now, so in a classical physics, right? Classical physics, okay, if there is a particle of mass m which is affected by some force, is going to create an acceleration, okay, which is defined by Newton's second law, F is equal to ma. Okay, so classical physics, the dynamics of the system, described by Newton's second law. Okay, but when it comes to quantum physics, okay, where wave function is used to represent the quantum system, not a position only or not momentum only, in that case, what is the dynamical equation which describes the quantum system? So quantum physics or statistical physics answers that using something called Schrodinger equation. Schrodinger equation. So remember, somebody who doesn't know what is Schrodinger equation, don't worry. It is in a way equivalent to Newton's second law. It is just like Newton's second law. Okay, it is just as Newton's second law. So what is the Schrodinger equation written in general? Is it is written in terms of eigenvalue equation. Okay, it is actually eigenvalue equation. What is that? Is you take the Hamiltonian of the system, multiply the Hamiltonian of the system to the eigenvector or the quantum state. It is going to give you the quantum state represented by eigenvalue, which is E. So you take the operator form for everything. So let's say quantum state is represented in some sinusoidal form, okay, in one dimension. Let's say if I want to represent in all the three dimension, let me write that, which is which is psi r comma t, which is equal to E into psi r comma t. Okay, where r is the vector having all the above degrees of freedom. Okay, all the degrees of freedom I just specified here. You see what are the degrees of freedom? Qi, Pi, spin degrees of freedom, and every other degrees of freedom were captured in the R. Okay, now the Hamiltonian of the system is just like energy of the system. Hamiltonian of the system is equal to kinetic energy plus potential energy in operator form. So operator form is just like some operator which is going to act on something. Okay, so kinetic energy usually is equal to half mv square, right? So I just multiplied by mass divided by mass. I'll have m square v square by 2m, which is linear momentum square by 2m. Okay, now when the variable from macroscopic system to microscopic system it transforms, means classical to quantum transition, okay, happens by treating the variables by its operator form. Okay, what is that is, so momentum operator, let's say in the x direction, linear momentum operator is represented by minus ih cross dou by dou x partial derivative. Okay, similarly position momentum operator in y direction is derivative with respect to y. Okay, momentum operator along the z is minus ih cross dou by dou z. Okay, so if somebody asks me how did you get this operator form, you can actually derive this operator form using simple wave mechanics or the waves. Okay, I'm not going into the details. Okay, so straight away I will just write what is the p square. P square would be minus h square dou by dou x square minus h square dou by dou y square minus h square dou by dou z square. That is the operator form of p square, which is going to be substituted at the top. Okay, so kinetic energy expression I will have, which is minus h square by 2m, okay, dou by dou x square plus dou by dou y square plus dou by dou z square. Okay, so dou square, I'm sorry, so which is h kinetic energy, h part of the kinetic energy, okay, or kinetic energy part of h, and now okay, this is kinetic energy. Now what is the potential energy? The potential energy is, let's say electron is existing in the combination of surrounding, okay, surrounding atoms or surrounding electrons. Okay, right? So now the potential I can't specify exactly because how many atoms are around, all those things, what electric field they are executing, and what magnetic field something is charging is moving, it is going to execute some magnetic field. So I'll just specify that as some kind of a U, potential energy at some position, okay, at some TA. Okay, so this is a potential energy of the system. Now what did I had earlier eigenvalue equation? H psi is equal to E psi. So let me write down that explicitly now. H cut whole square by 2m dou by dou x square plus dou square by dou y square dou square by dou z square. Okay, and psi r at some term t, okay, plus u r comma ti into psi r comma t is equal to e into r comma ti. Okay, let's put hat over I. Now, the energy also becomes an operator form in quantum mechanics or quantum physics, that is IH cross dou by dou T. So, just if somebody wants to know, as you know, energy is H mu, which is equal to H cross or H cut into omega, right? So, what is angular sorry, frequency? Frequency is units of 1 hour time period. So that is what I am having here. That is the easiest understanding one can have. Remember, we can derive exactly how E takes an operator form. Okay. Okay. As additional material, I will add to my lecture notes. You can just check that. I'm not going to I'm not going to discuss that. Okay. Now I have a even operator form for the energy. Let me write down that. Okay, which is equal to IH cross dou by dou T. So this is the Schrodinger equation, which is eigenvalue equation, just like value equation, just like Newton's second law, describing dynamics of the system in space and in time. Okay. Now, for the time being, let's say we were able to solve this differential equation. Okay. So how are we going to solve the differential equation? So for the time being, what you can do is you assume that on the left hand side, the entire thing is in the Hamiltonian form, which somebody has given you some kind of a matrix. Okay. So H is given as a matrix. On the right, I have operator form of the time. Okay. Okay. So now you can rearrange this into the equation where I can integrate. Let's say, let me do that. So dou Ri, so the R divided by R comma T equal to IH cross, right? So okay, not minus IH cross, okay, H into D dot T. When you integrate, what you get is on the left hand side we get a log or a natural log of psi r comma t, where let's say time running from some 0 to t is equal to minus IH cross into t. Okay. Now, if you specify the time limits inside the integrand, sorry, the resultant, I'll have psi r comma t divided by psi r comma 0, which is equal to minus IH cross h into t. Send the log to the other side. What you will have? You will have quantum state at later times is equal to exponential minus IH. Okay, I'm sorry, I missed Planck's constant should be in the denominator. Okay. 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 Right. So Planck's constant in the denominator, and this is what I will have. This is as a result of this differential equation from the different Schrodinger equation, where H is explicitly not expressed in terms of momentum or in terms of potential. So in this case, I'll have this, where this is a unitary operator which relates the system from 0 to some time t, so which is minus IH t by H cross. Remember this. Okay. So if I have explicitly expressed in terms of momentum and potential, in that case, I'll have a differential equation solved even in the spatial domain. But right now we are not doing it. Depending on the available information only, we will solve. Okay, right. So this is how I study the dynamical system of a quantum using statistical physics or using dynamical physics. Okay, right. Now the position and momentum and time domain we just saw. What are the other domains? That is spin degrees of freedom. So what is this spin degrees of freedom is? The spin degrees of freedom is the system is having spin plus half or minus half. Okay, so actual intrinsic spin magnetic momentum is actual intrinsic spin magnetic moment. Magnetic moment would be half into Planck's constant. Okay, so ms stands for plus half, means spin up. Ms is equal to minus half, means spin down system. Okay, it is just like the electron revolving in a clockwise direction or anti-clockwise direction. Okay, I just so this is anti-clock, this is a clock, electron revolving in the clockwise. So for us, usually we take a thumb rule. The curling of a finger shows the direction of positive charges motion, and thumb would show the direction of the momentum. Okay, right? So angular momentum, I mean. So the spin here in this particular case, right now, for the anti-clockwise, so you show the positive charges will be moving in opposite direction, opposite to the motion of the electron, and thumb would show into the surface. So into the surface is represented by cross mark. So the angular momentum is into the surface. Okay, right? And here angular momentum is out of the surface. Out of the surface. Okay, right? So if I take out of the surface is a plus half h cut, here it is a minus half h cut or h bar for the ms value, the degrees of freedom in the quantum system description. Okay, so as such, there is no dynamical variable or a derivative with respect to spin. Only derivatives exist with the space and time. So we will not worry about the derivative with respect to the spin variable in the case of quantum systems. Okay, now, okay, and since I want to solve explicit Schrodinger equation, okay, so not just only time derivative, let's say I want to involve the spatial derivative, which is very difficult to do, but there are shortcuts to do. Let's take an electron in an atom, okay, where the quantum particle is confined within an atom. What is the confinement? Electron can jump into n equal to 0 level or exist in n equal to 0, jump to n equal to 1, jump n equal to 2, and so on n equal to 3. It can jump between these two levels, these few levels. So what we do? We will convert this Schrodinger equation into harmonic oscillator form, that is called quantum harmonic oscillator. Quantum harmonic oscillator. Okay, the moment you convert to quantum harmonic oscillator, what happens is the energies with this which the system could exist is obtained as E of n, where n stands for the orbit number. So energy in each orbit is simply equal to n plus half into h cut omega, where omega is the angular frequency with which the system is rotating in that particular orbit. Okay, So the angular frequency is related to angular momentum and the velocity of the system. Remember that. Okay. So where here n is called a principal. Okay, it's called principal quantum number. Okay. So principal quantum number of the system would describe where the system is existing in a given time. So if there are n particles, I am considering to do a quantum computing. Okay, so there may exist n1 in principal quantum number with n1, so n2 and so on, nn. Okay, so where does the nth particle would exist, where does the second particle would exist, or the electron would exist, is specified by the principal quantum numbers of specific particle. Okay, very important, right? Fine. Now, so just here I was talking in terms of particle inside an atom or electron inside an atom. Let's say if I just take the electron outside, electron taken out, okay, taken out and put into a box of zero potential, okay, which is easier now. Okay, zero potential. What I'll take, I'll knock the electron out of the atom and put it inside a box. And remember, this box is not like a two-dimensional box. Let me draw a one-dimensional box. What is that one-dimensional box is? Electron would only able to move left or right in this one-dimensional box, where position x equal to 0, x is equal to 1, only between these positions the particle would exist. Okay. Now, in this case, just now I said the potential inside a box, potential inside the box is 0. Okay, is 0. Potential is inside the box is 0. Right, U is 0. In that case, how should we deal with this system? Now let me write down the Schrodinger equation explicitly now. H square by 2m dou square by dou x square dou square by dou y square dou square by dou z square, quantum state in 3 dimension x, y and z, but here the system is only can move in x direction, so I'll not worry about variation in the x direction, variation in the z direction I'll not worry, which is simply equal to E into psi of x. Okay, now let's say if it is allowed to move in x and y direction, I have to bring these things into the picture. Okay, if not, so I'll simply have a second order differential equation which is appearing like this. Okay, you can simplify this differential equation into linear differential equation as dou square by dou x square psi of x plus 2me by h cut square into psi of x is equal to 0. This is a second order linear differential equation. Second order linear DE. So this differential equations usually possess a solution. These DE possess sinusoidal solutions. Okay. Now the question is, for sure, these solutions will have some A into sin kx solutions. What is the K here? K is square root of, or K square, let me say K square. K square is some kind of a propagation vector which is equal to 2me by h square. Okay. If you want what is a K, you can just take a square root. Okay. Now, if you just see this sinusoidal differential equation solutions, now if I plot, okay, so it is going to give you a nice sinusoidal solutions. Now, if you just see at the boundaries, the particle is not going to exist because it's a wave function is going to cease to exist there. Means wave function is having no deviation. So at x is equal to 0, x is equal to L. Okay. So I don't see any variation in the wave function which is 0. So what I will have is sine kx going to 0 at x is equal to 0 and x is equal to L. So for sure x is equal to 0, sine kx is 0, but for x is equal to L, I have to find out. So sine L k into L is 0 implies k into L is some integral pi. Okay, so where k would be n pi by L. So if I'm writing only for x dimension, I'll write Lx kx. So therefore, the solution of quantum state would be, okay, some amplitude, let's say, we don't know right now, sine n pi into Lx into x, okay, where kx square is 2me by h square. Okay, as if you want to know what is the energy of the system, you can just write in terms of kx square h square by 2 into m. Okay, so h square k square into 2m. By the way, I know what is a kx. So let's put what is a kx. Kx is n pi Lx whole square. Okay, so you just do h square by pi square 2m Lx square, okay, into n. So I'll to subscript x stands for the x dimension. So energy with respect to x dimension coming out as h square pi square 2m Lx square into nx square. Okay, so here nx is principal quantum number again. Principal quantum number. Okay, so this is how we will deal the system, whether quantum mechanically or classical mechanically. Okay, or are we dealing with the system in collection of many things which are not interacting? All those things we have dealt today. Okay, so I'll stop at this point. We are actually crossed 5 o'clock. So in tomorrow's class, what we'll do, we'll go a little bit more in depth about the postulates of statistical physics or thermodynamics laws of statistical physics, how we can incorporate to study the quantum system in general. Okay, so thank you so much for listening. I understand there is so much of disjointness with going back and forth between classical to quantum. What I urge you to people is, I'll be uploading my class notes. You please go through the class notes. You will understand. Okay? Yeah, thank you. So I'll hand it over to the academy.
Yes, sir. Am I audible, sir?
Any questions, you can post it. I will be happy to answer. So there is one question by Priyaji again. What was the question? Okay, let me see the question. Okay, let me see from back. Is there any question? Then I'll come back here. Okay, let's see the Priyaji question. How can we represent the equation from equation forms spins which are flipping in Ising model as a quantum model? Oh, okay. So there is a Ising model itself, a mathematical statistical model. So using that, we will study this mechanically the systems. So yeah, we are not getting into that level of details, which is required for a later level. But as of now, we are only dealing systems are individually not interacting. They are weakly interacting. In that way, I can just simply treat them as a individual harmonic oscillators. Okay. So Ising model is something, there is an interaction exists between them. When it comes to quantum computing, so we can write the Hamiltonian for the Ising model in terms of quantum gates of interactions. Okay. So there is a X gate, Y gate, and Z gates are used to represent the Hamiltonian. And the moment you know the Hamiltonian, you can write the eigenvalue equation H psi into E psi. Okay. So let me write that. Okay. Just so for Ising model, okay, so the Hamiltonian has to capture the information of interactions. As you said, the spin interactions could be possible. Okay, right? So which is addressed by representing in terms X gate, Y gate, and Z gate. Z gate representations. So once you, by knowing H, you can have quantum kets is equal to energy operator into quantum gates. So this is eigenvalue equation. Okay. By studying the eigenvalue equation, you can find eigenvectors. What are the vectors? I can have vector psi1, psi2, and so on, psi n, corresponding eigenvalue e1, e2, and so on, en. So this is how we will study the Ising model system. There is a system with Ising model. Okay. Yeah. Yeah. So thank you, Anandji. Statistical physics to quantum mechanics. Yeah. So we are actually fluctuating, like a shifting between each other. Can you put some light on mixed states associated density matrix with examples? Okay, so good question. So mixed state. What is a mixed state? So the mixed state means we already had a figure. Okay, let me use that figure. Long back we had. Okay, just a minute. Yeah, this is a figure I have. So this is a combination of many groups of atoms creating a mixed state. Now, let's say all the systems are behaving like pure system. Okay, right? So pure system. Okay. So in the pure system, what is that? All the states or all the systems are represented by same quantum state. Same state. Okay, right? All the systems are represented by same. In that case, I'll have a density matrix, simply outer product. Okay, right? So now, for example, I'll have quantum state representation in terms of density matrix like this. Okay, now what you see is a mixed state with a combination of various density matrices where I runs from, let's say, 1 to n groups. Various n groups are there. In this case, if you just say, if you try to find the square of a density matrix, okay, so here in this case, the square of a density matrix is actually density matrix as it is. You know why? In a pure system, if you just take rho into rho is, okay, so the inner product between system with itself is 1. So I end up with outer product between quantum state to quantum state, rho. But when it comes to mixed quantum states, which is not equal to its shown density matrix. The square of a density matrix is not equal to density matrix. So that is the one way of saying system is not mixed, sorry, not pure. Okay. So in the pure case, what are so in the pure case, I would say system is existing in only one form. In a mixed case, what I see, system would exist in various combinations. So the example which you asked me is, let's say I take here there itself, there is a one group of system behaving with 40% and 60% ground and excited. There is another system 41%, 59%. There is another system, a group of systems 42, 58. So likewise, I have so many combinations of groups of atoms, group 1, group 2, group 3. Okay, quantum set psi1, quantum set psi2, quantum set psi3. So all together creates a large density matrix rho where the system to fall into particular density is given by probability P1, probability P2 and probability P3. So that is what the mixed states and the density matrix associated with that mixed state. Why the density is coming, the word density is coming means what is the chance of a particular atom, if I pick by closing my eyes, what is the chance of that is falling into a particular dense of group, that is where it is called a density matrix. So now density matrix is coming, I'm actually getting outer product leading us to a matrix. So that's why the matrix word is coming mathematically. Okay. So the real world example would be a qubits which you have taken. Some of the qubits are not behaving as per your requirement and some are behaving. That is a real world example of mixed quantum system represented by a density matrix. Okay. Okay. So Majumdarji, I think you can take over. I don't see any more questions.
Yes, sir. I think most of the questions are already considered. So thank you very much, sir. Actually, I have seen the comments continuously. The students have been very much engaged with your session and they have really enjoyed. We also here, our students are also sitting here. We also enjoyed. So thank you very much, sir. By the way, for tomorrow's session, I think we'll start at 3:30, sir, because you will have
Yeah.
other engagement, right?
So
So,
tomorrow I will be joining at 3:30 sharp. So
yes.
maybe you can wait for 5 minutes. 2:30, sorry, 3:30 or 3:35 will start. Okay.
Right, sir. That would be fine. So
Yeah.
participants kindly note tomorrow's time change. It's only for tomorrow. It would be 3:30, but plus minus 5 minutes we can consider. So that's that, and other things we have already discussed. So thank you once again, sir, and we'll see you tomorrow with another very engaging session and important session to be precise. So we'll see you tomorrow. Thank you,
Yeah.
sir. Thank you once again.